So we're going to talk about numerical integration, and that's going to entail three different rules. The first one is going to be the midpoint rule. The second one will be trapezoidal. And the third is going to be Simpson's rule. All right, so these three rules of integration will allow you to integrate because whenever you cannot find an antiderivative. So if you need a definite integral, we have kind of sort of lied to you a little bit through all this time. You've gotten the impression that now we're able to integrate pretty much anything. But the reality is that the number of, or the set of functions that we can find antiderivative for and then use the fundamental theorem of calculus for is somewhat limited. So whenever we cannot find an antiderivative, we cannot use the fundamental theorem of calculus. Say if you want to compute the integral from a to b of a function, and at that point, well, you are left to doing approximations, and these approximations will be through numerical integration. So the first thing you're going to do is you're going to consider the midpoint formula, which is the limit as, let's say, n goes to infinity, and of the sum of I equals 1 to n. And I'm going to go do delta x, which is going to be, as always, your width of your rectangles. In this case, b minus a over n. I'm going to do uniform rectangles, and then f of what I'm going to call c sub I, or we could call it lowercase m sub I for middle. And so delta x is as usual, b minus a over n. And then what ci is going to be is just going to be the arithmetic mean between xi minus 1 and xi. So I'm going to draw a picture as to what that means. So basically, if you have your area here that you want to compute, what you're going to do is you're going to separate. In this case, I'm going to do 4 subintervals because, well, I cannot draw too well, so I'm going to do 4. So this would be your x1, x2, and x3. A is equal to x0 and b is equal to x4. So there are your 5 endpoints to the 4 subintervals. So what I'm saying here is that your ci you're going to be picking for midpoint formula would be right at the middle. So the average between, in this case, a and x1, which would be x0 and x1. This one would be your next point. This would be your next point. And so these guys are going to give you the height of the rectangle you're drawing. So you see, before when we did rectangles, we had the issue that we were kind of leaving some, we're either doing lower or upper rectangles, and we were leaving spaces that, say, if it was lower, we were leaving spaces we were not covering, and if it was upper, we're covering extra. But in this case, you kind of have this sort of bow tie situation where you're taking extra that you're adding extra that that is not in your area, but you have this other stuff that you're under counting. So just by doing middle, the rectangles based in the middle is going to give you a lot more. Wow, that's really crooked. Oh well, that rectangle is going to be very, very uniform, right? Yeah. So it's going to give you a lot more precision just from that. Or you're going to get closer to your actual area by doing middle rectangles. So that really doesn't take any kind of work. It's not hard at all to do. So let's just do a quick one. So and by the way, I put the limit, and this would be the exact area. But what I meant to, or what I should have done, is define your m sub n, because these are gonna be approximations. So sum from I equals 1 to n. This would be the exact definition. It's just a Riemann sum for it, and so that would definitely work. But in this case, we want approximation. So you will say approximate using midpoint formula for, say, 4 rectangles I did here. But so So that's going to be these are going to be all your formulas right here. I believe I should also mention one thing here. So remember that xi was going to be equal to x naught plus I delta x. So we can plug here ci would be equal to x naught plus I minus 1 delta x, and then that's this term here, plus x naught plus I delta x all over 2. That's a lot of stuff. But you see, when you add x naught and x naught divided by 2, you get 2x naught divided by 2. That's still an x naught. So now here, we're going to have I plus I. So we're going to have 2I. I guess I need a plus. Minus 1 over 2 delta x. So you could also use this formula to compute your CIs. If you don't want to write every xi and then do your averages, you could use this formula as well. All right, but these are the ones that you would need. So let's go ahead and do an example real quick. So let's say that we want to compute, so approximate the area let's say from 0 to 1. I don't know, let's do something simple. I just want to show you the mechanics, how it works. So I suppose I'm going to do plus 1. You see what I'm going to do? I'm going to grab this one and turn it into a 1, because it's also ugly. So 1 minus x squared. So just a parabola that opens down with intercept 1. So I have an area there to compute. So approximate this integral by using the midpoint formula. Or approximation, if you will. Approximate using approximation, maybe not that great. With n rectangles, and n is going to be what, 4? Why not? So let's go ahead and do that. So what we're going to start with is going to be take our delta x. So delta x is going to be 1 minus 0 over b minus a over n. In this case, it's going to be 4. So I'm going to have that my delta x is 1/4. Graphically, what that means is I have my graph between 0 and 1, just a parabola that opens down. And I'm going to be dividing, so between 0 and 1, I'll divide it into 4. So the first term is going to be 1/4. So the first so interval is going to be 1/4, 1/2, 3/4, and 1 3/4, something like that. All right, so those are going to be my endpoints. So my CIs, I could start writing them here. So the first one is going to be the number in between these two. So the average between. So 0 plus 1/4. So C1 is going to be 0 plus 1/4 all over 2. That's going to give you 1/8. So that point right here, that's going to be your 1/8. That's a pretty terrible arrow. Okay, I made it even worse. Let's see where it was. So 1/8. All right. So C2 will be the average between 1/4 and 1/2. So 1/4 plus 1/2 all over 2. And you say, well, if you can just do the average, why did we even do this part? I'm going to use that whenever I put it in Excel. So I'm going to show you how to do this calculations in Excel to make it a lot faster for the homework. And truth to be told, if you were to actually need to compute an integral, you would not do this by hand. So I'll teach you how to do it with Excel, and of course you could program it in Python or R or whatever software you like, so whatever language you like. So anyway, so 1/4 and 1/2. This is going to be 2/4. The 1/2, so 2/4 plus 1/4 is 3/4 over 2, still 3/8. So that's the next term there. So it's going to be this guy here is 3/8. Let's do the next one quickly, the next two. So C3 is going to be 1/2 plus 3/4 is the next one over 2. So this again 2/4 and 3/4 is 5/4 over 4 over 2, sorry, 5/8. That's going to be my value here. And then I'm going to have C4. Don't say that out loud in a airport. 3/4 plus 1 is 2. This is 4/4 and 3/4 is 7/4 over 2, 7/8. All right, so those are my values here in the middle. And so what I'm going to do is I'm going to draw the rectangle that is going to have height corresponding to this value. Sort of like that. Then I'm going to grab the rectangle that has height given by this value. And then the one here. Up. Fail. There. Much better. And then this one at this height. So what that means is that to compute each height, I need to find f of C1, f of C2, f of C3, and f of C4. And I need to add another page. And so I'm going to write it here. So somehow I thought that I was going to be able to fit every method in one video. Silly me. I'm going to go ahead and compute it. I'm going to show you how to do it with Excel, and I'm going to then wrap the video up there. Anyway, so let's go ahead and compute f at each one of these things. So notice here my function is 1 minus x squared, so I'm going to be plugging C1 and I'm going to square it. So 1 minus C1, which is 1/8. I'm going to square that. That's going to be, when I square, I'm going to get 64. So I'm going to have 1 minus 1/64 is 63/64. 63/64. Then for the next one, I'm going to have 3/8. Square it. That's going to be 9/64. So 1 minus 9/64 is going to be 64 minus 9, which is going to be 55/64. Then this one's going to be 1 minus C3, which is 5/8 squared, and that is going to be 25. So 64 minus 25/64. So 64/64 minus 25. So if I take 24, it's going to be 40, so 39/64. And lastly, this 7. So 1 minus 7/8 squared. That's going to be 64 minus 49. So if it's 50, it is 14. So 15/64. All right. So now what I have to do is write the formula for the area. The approximation, I suppose. Mn is going to be the sum I equals 1 to 4 of delta x f of ci. And as you know, I can always factor out my delta x. My delta x, if you remember from here, is 1/4. So 1/4, and then I'm going to sum all the areas. So I guess the 64th can also be factored out, if you guys don't mind me doing that. So I'm going to factor the 1/64th out, because I don't have to write it over and over. And then I'm going to add the height. So 63 plus 55 plus 39 plus 15. That's going to give us what? I'll have to check my number. So 172 over here, 16, 24, 256, which is approximately equal to, I'm going to put in a calculator, 0.672. But now this one, the function I chose is straightforward to compute the integral, the exact integral by the fundamental theorem of calculus, right? Because that would just be integrating here, you get x minus x cubed over 3 between 0 and 1, which is 2/3. And 2/3 is approximately 0.66 periodic, so 6/7 roughly. So you see we're not too far off. Of course, you say, well, this took you 2 seconds to do versus with the one above. But remember, I'm talking about whenever you cannot find an antiderivative, so you cannot use the fundamental theorem of calculus to solve it. So I'm going to show you how you would put this one in the how you put it in the computer. So I'm going to show you how to do it with Excel. All right, so remember we were going to integrate this or approximate the integral with the midpoint formula for in between 0 and 1. So I'm going to start with my x coordinates, so I'll put them here. So I'm going to start with, say, 0, that's the first one, and then I'm going to do one thing. I'm going to pick my delta x. So let's insert a symbol here so it looks nice. So I'll do my delta x. You don't have to do this. Where's delta? I cannot see it. Well, that was unnecessary. Here's delta. All right, insert. So delta x. Done. So delta x, for some reason it just became giant. So delta x, I'm going to pick it to be, and I'm going to set equal to write a formula, parentheses 1 minus 0. That's my b minus a over n. So at the moment, because we already did 4, let's do 8 rectangles, just because with the computer it's a lot easier. So I'm going to do this. I'm going to go x, I'm going to start with 0, plus, what? Plus this one. But I want this cell to be fixed all the time. So I'm going to put dollar signs in front of both the cell column and the cell row. So that's going to fix that amount. So you see when you scroll your formula, you're just going to be adding the same amount, 0.125 all the way. And you're going to continue. You're going to just scroll until you get to 1. These numbers I don't care because I'm going from 0 to 1. If I would have done 10 rectangles, I would have had to do a few more cells. So that is my first column right here with the x's. Next thing I'm going to do is I'm going to evaluate the function at each one of those values. However, this is not quite what I want to do. I want to do my CIs. Remember, we had the x's and we needed the CIs. So I'm going to do the CIs. I'm going to put the average between these two guys. So start with a parenthesis, sorry. So I'm going to do this cell plus this cell divided by 2. That gives me the average of these two guys. And I'm going to just scroll all the way to the bottom. This is just what I'm doing is xi plus xi minus 1 over 2. So I just did the average right there. So these are the numbers I need. You see, you're always going to have n plus 1 x values, and you're gonna have you're gonna need just n of them. So it's always gonna be one that is gonna be left there. So you're not gonna use that. Now I'm gonna evaluate, as I said, my function at that value. Oh, pretty neat. Not what I wanted to do, but it's okay. So I'm going to do 1 minus, I'm going to plug in the equation, 1 minus, and whenever I need an x, I'm just going to grab that CI, and in this case, I'm going to square it. So this is just 1 minus x squared. I'm grabbing the cell to be whatever the x value I need. So I want to just scroll through this. And let me check one thing. Yes, that is correct. All right. I don't know what I'm doing. And now I have all this, and what I'm going to do is I'm going to add them all together. I'm going to do the sum of all these. So what I have written there is just the sum inside of the parentheses. But remember, that I still have to multiply times delta x. So this is going to be the sum inside the parentheses. And now my approximation, my m sub n, is going to be this, in this case m sub 8, is going to be this quantity times my delta x. And that gives me my 0.6679 something. Remember that the one that we computed exactly was 0.6666 periodic. So it was, so in this case, we have accurately approximated to the second decimal. So that's how you do it with Excel. I'm gonna keep this Excel sheet open, and I'm gonna call this one midpoint, and then I'm gonna keep adding then trapezoidal rule, and I'm gonna then add Simpson's rule, and I'm gonna post it to our Canvas page. All right, so that's gonna wrap up this video. Uh, Thank you so much for watching.